rational functions. It's everybody's favorite. Well, my favorite. Okay. So basically, you were introduced, again, you hear me saying this a lot in Precalc honors. You were introduced to this last year, blah, 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 right? A rational function is basically a quotient of two polynomial functions. So you take two polynomial functions, divide them by each other, and you get a rational function, right? The domain of rational functions is all numbers except whatever values make the denominator 0, okay? So all real numbers excluding the ones for which the denominator is 0. A characteristic of rational functions is that many have asymptotes, either vertical, horizontal, or both. So we're going to remind ourselves about vertical and horizontal asymptotes today. Okay, so a vertical asymptote looks like this. So basically an asymptote is, you've heard that word last year, yeah? So it's an imaginary line that the graph comes exceedingly close to but never touches, right? Okay. So here's a vertical asymptote, right? You see how, like the graph will come near but never touch it. And then you could also have a horizontal asymptote. Okay, so how do we find horizontal or vertical asymptotes? All right, let's focus on horizontal asymptotes first. To find the horizontal asymptote, theoretically, it's the end behavior of a function. Remember when we learned about end behavior, it was the limit as x approaches infinity? And so we said that, like there could be a trend, right? So for example, this one here, as x approaches infinity, what's happening? The graph is leveling off at y equals 6. So that's the horizontal asymptote, yeah? So how do we find it when we have a function? Well, what you have to do, all you have to do is compare the highest degree in the numerator with the term with the highest degree in the denominator. All right? So now, if the numerator has a lower degree and the denominator has a higher degree, then automatically we say the horizontal asymptote is y equals 0. Okay, you have to have the y equals there, not just 0, otherwise it's always points off. Okay, so for example, suppose f of x is equal to 5x squared plus x over 3x cubed minus 1. Okay, all you do is compare this and this term. More x's on the bottom automatically means the horizontal asymptote is y equals 0. All right? Okay. If they have equal degrees, then the horizontal asymptote is the reduced form of the equation. So for example, if f of x is 5x squared plus x over 3x squared minus 1 this time, okay? Compare the numerator and the denominator. They have the same degree. So the horizontal asymptote is just the reduced form of this fraction, which is just 5/3. All right? So y equals 5/3. And then if there is a lower degree on top, higher on the bottom, there is no horizontal asymptote. Right? Okay. Now, disclaimer. If the numerator has a higher degree by 1, then there is what we call an oblique asymptote. It is an asymptote. Technically, it's not a horizontal asymptote, so that statement above is still true. Okay? We'll get to that later. All right. So that's about horizontal asymptote. It's a different process than a vertical asymptote. To find the vertical asymptote, it's really much simpler. You simplify the function. That's important. Okay? Then you find the zeros of the denominator. Okay? And this is, make sure you're careful here. This is the zeros of the factors which cannot be eliminated. All right, so let's do this Again, so this is basically an infinite discontinuity, right? What we were doing before, that's an infinite discontinuity. Okay, so let's do some of these. We want to find the domain and the vertical and horizontal asymptotes of these functions. So, domain is everything except where the denominator is 0. So for the domain, let's set the denominator equal to 0. Okay, solve it. X squared is 17. So x is plus or minus root 17. So the domain is all numbers except for this one. Okay, so it's negative infinity to negative root 17, negative root 17 to root 17, root 17 to infinity. That's the domain. Questions? Okay. What's next? Vertical asymptote. Okay, so for the vertical asymptote, again, we're just, for the vertical asymptote, before you do that, can you factor the numerator or the denominator in a way that things will cancel? No. So just set the denominator equal to 0. We already did that. We know x is plus or minus root 17. And that's good enough for the vertical asymptote. Okay? So yeah, it's a similar process. Okay, horizontal asymptote, take the higher, degree terms. So since they're the same, y is equal to 5 over 2. Okay? For this one, you look at the original function if you had factored. Okay, so let's do another one. Can we factor the top and bottom in any way? No. So let's do domain. 2x squared plus 1 equal to 0. X squared is negative a half. You take a square root. X is plus or minus the square root of negative a half. So how much is that? 9. Huh? It's an imaginary number, right? Plus or minus I root 1/2. So what does that mean? That means there are no real numbers for which the denominator is 0. Correct? Think about it. Can you put in a number for x and make the denominator 0? No. So if the denominator can never equal 0, are there any issues with the domain? No. So what's the domain? All real numbers. Okay. Okay. All right, so what about the vertical asymptote? Huh? There isn't one. Okay. Horizontal asymptote, what would it be? Y equals 2. Exactly. Okay. Okay, so here, what's the domain? You can tell me without even doing any work. Where is the denominator 0? Huh? For this one? Where is it 0? Where is the denominator 0? At 17. Right? So if you do 2x minus 34 equals 0, x is 17. So that's the domain. So vertical asymptote is x equals 17. Horizontal asymptote, y equals what? Well, is there a horizontal asymptote? None. Huh? It would be an oblique, so there is no horizontal. We haven't learned how to find oblique yet. Okay. Next one. Okay, so here is one where you can, this one you can factor, right? So let's factor this first. How do we factor? X plus 4, x minus 2. Okay. Okay, so we can do the domain, right? Negative infinity to negative 4, negative 4 to 2, 2 to infinity. Okay, now, Do any of these terms cancel?
Yeah.
No. So they're both going to give you a vertical asymptote, right? They're infinitely there. So that's an infinite discontinuity. So it's x equals 2, x equals -4. And now, for the horizontal asymptote, go back to the original function, right? And so it's y equals 0. Cool? Okay? All right. So, let's graph these. No longer are we going to graph with the calculator. Now we're going to graph by hand, because that's what we do. Okay? All right. So, to graph anything in math, you always have to look at discontinuities and trends. All right? So, you have to look at the domain, where are their asymptotes, and all that beautiful stuff. Okay. One thing about horizontal asymptotes. Okay, so a vertical asymptote is a point where the graph is undefined. There is no crossing a vertical asymptote. It is like a wall. You cannot cross it. A horizontal asymptote is different. Remember what we said about a horizontal asymptote? It's defined as the limit as f of x approaches positive and negative infinity. So, horizontal asymptotes only take effect at the infinities. That means you can have a graph, right, with a horizontal asymptote here, right? The graph can cross the horizontal asymptote 1,000,000 times in the middle. It's only at the infinities that they take effect. So it's possible to have a function that looks like this, and then at the infinities, it follows the asymptote. Okay? All right. So let's do this. So what's the domain here? Well, let's factor this first. Always factor and have it ready. All right, so we know the domain, right? I don't have to go through too much of that. Okay? All right, somebody tell me what the vertical asymptotes are. Raise your hand and tell me. Raise your hand. What are the vertical asymptotes? Max, I'm going to pretend you're raising your hand.
Yeah.
Oh, okay, good. Sorry, I wasn't sure.
2.
And?
-2.
But x equals 2 and x equals -2, right? So that's where that goes. Okay? All right, somebody raise your hand and tell me if there are any horizontal asymptotes. Yep.
0,
right? What equals it? Y equals 0. Good. Here. Okay. Now, what we have is 3 regions of this. All right? What I also want you to do is find the zeros. Okay? How do we find the zeros? To find the zeros of a rational function, you basically set the numerator equal to 0. So x plus 1 equal to 0. X equals -1 is a 0 of this function. Okay, now, in Precalc, we want to look at the big picture, right? So we step away from the mundane plugging in points, except where necessary. Okay, so take a look at this. If this graph is going to follow the asymptotes to the, up and down here, then, and there is only one place that it crosses the x-axis, then if you think about it, the graph can either look like this, right? Because it only crosses once and it has to follow the asymptotes up and down, or it can look like this, right? So how do we know? Well, all you need is one test point. So pick a point in that region to plug into the graph. I would pick x equals 0, okay? So test point at, here, let's do this. x and y. So when x is 0, what's y? -1/4. Okay, so that means it's here. So that means now I know exactly how it's going to go. Yep. Okay, so like that. Okay, so how do the other parts of the graph look? Okay, have you ever played those video games where, like, when the character goes off the screen, it comes back from the other side, right? That's kind of how this is, right? So if the graph exits the screen here, it re-enters to the left, to the right of the asymptote from the top. So if it exited from the bottom, it comes back from the top. So now it's going to come back down, and then there are no more zeros here, so it can't cross the x-axis. So it's got to turn around and follow the horizontal asymptote on the other side. So it's got to come down, turn around, and follow the horizontal asymptote on that side. Similarly, on the other side of the asymptote, if it exited the screen at the top, then it has to re-enter on the bottom. Same way, it's got to curve and follow the asymptote. And guess what? This is the graph of this function. Do you see that? Did you ever think you could do this by hand? No, but look at that. You see that? Super cool. Yeah.
Is there a horizontal asymptote between -2 and 2?
Okay, the horizontal asymptote is y = 0, but remember it takes effect at the infinity.
Okay, so then
Yeah.
it's like it just skips that part. And,
Mm-hmm.
okay.
Mm-hmm. Yeah. The reason why I can do this is, remember we said, so when you have a 0 with odd multiplicity, right? It crosses the axis there and it changes sign there, positive to negative. But then a graph can also change sign at the asymptote. So that's what's happening here. Okay, let's do another one. Let's factor this. See what happens. This is x minus 4, x plus 3. Okay. All right, so we know what the domain is. It just doesn't exist at 2, right? Okay, so right now, go ahead, take 2 minutes, or 1 minute, and write down the vertical asymptote, the horizontal asymptote, and the zeros for this, please. But don't graph yet.
What's the exponent you're comparing it to in the bottom?
So vertical, you just set the denominator equal to 0. Okay? Madison, do you have horizontal?
9.
What do you think? It's a tricky one. Yeah.
I got 1/2.
How?
But because they're the same degrees, the coefficients of one another.
Right. So this is x squared on top. On the bottom, you have an x squared. So it's x squared over 2x squared. So y equals, so here it, technically speaking, it's the limit as x approaches infinity, x squared over 2x squared, and then you know the x squares cancel, so you get a half. So y equals a half here. Okay. All right. Raise your hand if you have the zeros. We're setting the numerator equal to 0 for these. Jesse.
X equals 4 and x equals -3.
4 and -3. Yes. Okay. So let's put all that down. -3, 4. And then I have a vertical asymptote just at 2. Okay. Now I have 2 zeros. Okay? Now I have 2 zeros. So let's take a look at what's going to happen here. Let's go to the right side. Okay, let's go to the right side. Let's test a point, right? If x is 3, right, over here, Okay, how do we do this? If x is 3, okay, look at the denominator. Is it always, it's always going to be one sign, positive or negative? Always positive because you're squaring it. So all you have to think about is the top. So if x is 3, in this parenthesis you get negative, positive, so that's negative, right? So when x equals 3, the value is negative. What about when x equals like 6? Let's just, you don't have to do more, but what about when x equals 6? It's positive. So we are certain now that this is going to look like this. Yes? Okay. Now, remember how at the asymptotes, I said it changed sign and it entered on the opposite side? Well, now this is a different situation. Because look, this is what I love about math. Look at how harmonious it all is. Look at where these asymptotes came from. They came from this term, and both of these have exponents of 1. So the multiplicities are 1, which is odd, right? Odd multiplicities. So the signs will change. But here, where does the vertical asymptote come from? Here. It's squared. What's the multiplicity here? When it's even multiplicity, remember how it stayed on the same side, it bounced back? That's what happens here. When it's even multiplicity, it comes back from the same side and it goes that way. Like this. Isn't that cool? Say yes. Yeah, there you go. Okay? All right, let me make that look. Yes. Huh? Yes, for the zeros, you always set the numerator equal to 0. Okay, so much for that. Next, I want to talk about oblique asymptotes. All right? So oblique means slanted, and back in the day in various books, it was also called a slant asymptote. Then they somehow now like oblique is the better term, whatever. Okay? So you get an oblique asymptote when the numerator has a higher degree by 1. So x to the power of 2 over 1, 3 over 4, blah, 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 okay? 4 over 3, I mean. Okay, so let's do this quickly. What's the domain? Negative infinity to... Right. Correct. Okay, what's the vertical asymptote? X equals negative 3. This doesn't factor, right? So we're not going to factor it. Okay, horizontal asymptote, none. Okay, but there is an oblique asymptote. Okay, here's how you find the oblique asymptote. Guess what you have to do? You have to actually do the polynomial division. All right? So you have to do either long division or synthetic division. Luckily, we can do synthetic division here. So let's do that. So we're going to have negative 3. 1, 1, negative 8. We're experts at this now, right? Except I guess I'm not. Okay, negative 2. What's this? 6. Negative 2. That's the remainder. Okay. For the purposes of this, throw away the remainder. Okay? What is this polynomial here? X minus 2. Y equals x minus 2 is the oblique asymptote. Okay? So, let's graph y equals x minus 2. You graph it like you did back in algebra. Okay, y equals mx plus b. So y-intercept, up 1 over 1. This is so exciting. That's an oblique asymptote, so we make a dashed line. What else do we have here? X equals negative 3 is a vertical asymptote. Okay, so the zeros here, you can't graph it. I mean, you can't factor it, so you have to do like the quadratic formula. Okay, so now look. These are harder to figure out, how it looks by hand, without a calculator. So to graph these, I'll allow you to use a calculator. However, I could still ask you to find the oblique asymptote. I can ask you all this on a non-calculator section. You know what I mean? And then to graph it, so here's how it looks when this is graphed. It's like this and like that. Okay? So look, same rule applies at the vertical asymptote. This has a multiplicity of 1. The graph exits the screen at the bottom, then it changes sign and it comes up here. Like, do you see the harmony? Right? Like, in no other field would you get this, right? This is a math thing, right? So, yes. Yeah. Okay. All right, questions on this? How is this looking? Okay, so what about holes? We'll do holes and then we'll stop with the rational functions. Removable discontinuity. Now finally it all gets set, right? Remember how before you're like, well, how do I find the horizontal asymptote? I'm like, just wait. So here it is. We waited and now we got there, okay? Yeah.
How would we find the zeros within a group?
Well, quadratic formula.
Oh, okay.
Yeah. Okay. So when the numerator and denominator have common terms which can cancel, that's where we get removable discontinuities, which you guys did on the final as well. And that's where we get tiny holes in the graph. So let's do this one. We can factor this. X minus 3, x plus 3, x minus 3, x plus 2. And yes, these cancel, so now I get x plus 3 over x plus 2. Okay, now, domain. For domain, you're going to look at this before it cancels. Because yes, this cancels, but if you go to the original equation, positive 3 still doesn't work. So it's negative infinity to negative 2. And to 3 and so on. Okay. Vertical asymptote. Which one is it? Is it the 3 or the negative 2 or both? Negative 2 only, because it never canceled. Okay. Now, we have a removable discontinuity at x equals 3. Okay, what's the horizontal asymptote? Look at the original function for the horizontal asymptote. Y equals 1. What are the zeros? For the zeros, this went away. So you only look at this, x plus 3 equals 0. So it's x equals negative 3. Okay, so x equals negative 3 is a 0. We have an asymptote. Okay, and now I'm going to tell you to do something. Let me put in the horizontal asymptote. Okay, so take a look. So this is how it looks. And then at x equals 3, there is a removable discontinuity, right? You have to figure out where that is. Yeah.
How do you know when we try and find an oblique asymptote?
When the numerator has a higher degree by 1. So it's like x to the 4 over x to the 3. Yeah.
So do we also know when there's like a section of the asymptote that is...
The asymptotes always take effect at the infinity. Always. Okay, so look. At x equals 3, there is a removable asymptote. But how do we know if it's here or here? Like there's basically a hole in the graph, but how do we know where it is, right? For that, you have to plug in a point, but it's very tricky because you have to do it mentally. You cannot show any evidence that you plugged in a 3, because technically 3 is a point where the function is undefined. Okay, but how are we going to find it? You basically, so at x equals 3, if you plug it in there, what do you get? 6 over 5. Okay, but it's illegal to plug in 3 into this function because technically it's undefined there. So you can't like have any evidence of it. Does that make sense? right? And then next year in calculus, you'll learn like limit notation, and then you can do it. But right now, like this, it's kind of illegal. So just do it mentally. And so here at x equals 3, and over here, you have that removable discontinuity. Oh, no, sorry. It's 1 1/5 here. Okay? So then we know how this looks, right? If it crosses there, then it's got to look like this, right? And then it's got to come back down from the, or come back up from the bottom and look like that.
And if there's like another vertical asymptote, then it'd be...
Yeah, then the whole thing would kind of be different because you would have to have a middle section.
Right,
yeah. Make sure this is visible. But what some students do, so what some students do is they do this and then they put, that's not good, right? That's no good. Okay? So what I would do is put the little circle there and then make sure your graph like doesn't touch it, like doesn't cross it. See what I mean? Math is very funny when it comes to like these things, all right? Okay, so I think this is a good place to stop. I know.